What's up, guys, and welcome back to this concept video on gravitational force fields. In the previous video, we went over a few concepts and we did some examples, the last of which was this example where we had multiple masses and we wanted to calculate the resultant force. Okay, so now I am going to go back and just discuss a concept that we touched on but didn't get into a lot of detail, which is interacting gravitational fields. Okay, so we discussed that there is some point where the net force is equal to 0 newtons. So essentially there's a feeling of weightlessness. Okay, so we want to try to determine where that is. Okay, but before we do that, let's try understand qualitatively where that could be. Let's say if we put the halfway point in here, so the distance between both planets is equal, is it going to be to the left of that line or the right of that line, or is it on that line exactly? Okay, so first let's put down the formula. F equals g m1 m2 over r squared. Okay, so if we have a mass, let's say we have some mass m2. Okay, so if it was right in the middle, the bigger planet is obviously going to have a bigger mass. Okay, so looking at our equation, the force from the bigger planet is going to be quite large. Okay, when compared to the smaller mass, which is going to have a lower mass. Okay, so the smaller mass will result in a smaller force. So we're going to have a smaller force to the right. So at the end of the day, what's going to happen is we're going to have this body accelerating towards the left, because we have unequal forces or unbalanced forces. Okay, so let's see what happens if we let's see what we can do. Let me delete this. Okay, so what happens if we put the mass to the left? Okay, once again, now I've decreased the distance, so I've decreased r, and I've increased m. So what's happening is my numerator is getting bigger, and my denominator is getting smaller. So overall, I am getting a bigger force. So once again, we have a very strong force to the left. And if we look at the right-hand side, what's happening is my r for the right-hand side is now increasing. So for the right-hand side, my r is going up, and my mass is going down. So my numerator is going down, and my denominator is going up, resulting in a smaller force. Okay, so at the end of the day, what's going to happen? My object is going to accelerate to the left once again. Okay, now let's look at the last scenario, which hopefully you guys are understanding will be to the right. Okay, so now let's see what we have. Okay, so if we look at the larger planet, okay, so we have a big M1, so we've got a higher numerator, and our r is also increasing, so our denominator is also increasing. So we have a relative force, and there is some point, okay, where on the left-hand side we have r getting smaller. Okay, so we have r going down and mass going down, but r is squared, right? So r goes down, so the numerator is getting smaller at a faster rate. So what we have is that these forces will actually balance each other. Somewhere in this region between the midpoint and the smaller mass, we will have a net force, F net, is equal to 0. Okay, so we want to figure that out. And to do that, let's get into an example. Let's see, let me just move to the right. Okay, so let's say we have two objects. Okay, let's say object A has a mass of, let's say 2000 mega kilograms, whereas object B has a mass of 10,000 mega kilograms once again. Okay, and their distance is fixed. So we have a fixed distance between A and B of, should we say? Let's say 1,000 kilometers. Okay, So at what distance between A and B is the net force equal to 0? Okay, so let's start off by drawing out the scenario. Okay, so obviously A is smaller than B, so I'm going to actually draw A as smaller, so A is there, and we have B, which is bigger. Okay, and we know that their center distances is going to be 1000 times 10 to the 3 meters. Okay, I'm moving this to SI units. I want meters as my units. Okay, I'm also going to do the same thing with their masses. I'm going to say this is 2000 times 10 to the 6 kilograms, and this is 10,000 times 10 to the 6 kilograms. Okay, so everything's in SI units. Okay, so I want to know the point, some point between these two objects at point, let's say point P. Okay, so at some point P, if we put a third object in there, into there, so let's call it object C actually. If we put object C in between A and B, there's going to be a 0 net force. Okay, so I want to determine the distance where that is. So I'm going to call the distance between A and C as x. Okay, so a distance x. And what does that make the distance between C and B? It makes it 1000 times 10 to the 3 minus x. Okay, does that make sense? So basically what I'm saying is this distance, let's say that's distance 1, that's distance 2, and that's distance 3. Distance 1 plus distance 2 is equal to the total, which is distance 3. And that's true because we have x plus 1000 times 10 to the 3 minus x. The x's cancel, and we're just left with 1000 times 10 to the 3. Okay, so once I've done that, I want to work out the forces pulling this to the left and C to the right. Okay, so I'm going to say, force, let's see, force AC. Okay, so force AC is going to be equal to G M A M C over R AC squared. Okay, and force BC is going to be equal to G M mass of B mass of C over R, distance between R and BC, all squared. Okay, so this is my force AC and this is my force BC. So for there to be a 0 net force, force of AC must be equal to force of BC because they're acting in opposite directions. Okay, so therefore I can equate these two. So I'm saying that FAC equals FBC. Okay, so if we do that, then what we're left with is we have the gravitational constant mass A times mass C over RAC squared is equal to G mass B mass C over RBC squared. Okay, and then we can cancel some stuff. So my gravitational constant cancels and my mass of C. Okay, my mass of C can get cancelled. So my mass of C's go away. Okay, so now I'm left with mass of A over R of AC squared is equal to mass of B over R of BC squared. Okay, so then what I can do is I can put in some values now. Okay, because I know the mass of A. What's my mass of A? Okay, so my mass of A is equal to 2000 times 10 to the 6 over R of AC. Okay, so R of AC, so the distance between R of AC, so distance between R of AC is equal to X. So I have a X squared is equal to 10,000 which is my mass of B, times 10 to the 6, all over my R of BC, which is this thing here, R of BC, the distance between B and C, which is, again, so it's a 1000 times 10 to the 3 minus x, all of that squared. Okay, so now what I want to do is get all my x's on one side, so I'm going to say 2000 over 10,000 is equal to, okay, these 10 to the 6's cancel, is equal to x squared over 10,000 over 1000 times 10 to the 3 minus x, everything squared. Okay, now I want to solve for x. Okay, x is the only unknown here. Okay, so how am I going to do this? Okay, so I can identify something. If I take this out, if I take these brackets out, remember everything in that bracket was squared. So I'm just going to take the squared onto the outside, onto the bigger picture. Okay, and then square root these sides. Okay, so when I square root the right hand side, I'm left with x over 1000 times 10 to the 3 minus x is equal to the square root of 2000 over 10,000, which is square root of 5 over 5. Okay, so I'm just going to leave it in that format for now. Yeah. Okay, now I'm going to multiply this up, so I'm left with square root of 5 over 5 times 1000 times 10 to the 3 minus square root of 5 over 5 times x is equal to x. So if I take the x's to the right hand side of the equation, I'm left with square root of 5 plus 1. So 5 plus the square root of 5 over 5x is equal to this whole number here. Okay, now I have x. I can solve for x very easily just by dividing everything by this term right here. So I'm going to take the left hand side, which is square root of 5 over 5 times 1000 times 10 to the 3 divided by this expression right here. And x is equal to, let's get this in meters first, 309,016, let's just say 7 meters. Okay, or we can get this into kilometers, so we multiply that by 10 to the negative 3. We can say x is equal to 309,017 kilometers. Okay, so that means this value right here, x is equal to 309 kilometers. And that means the other side was equal to 1000 minus 309 is 691 kilometers basically. Okay, so I hope that made sense, guys. Quite a lot of, actually not a lot of thinking. Once you get to this point, or that point, it's basically all just maths. Okay, so now we're going to move on to another concept. Okay, so we know we've already discussed the forces experienced by different planets, but let's find, we can actually get a equation for G, which is our gravitational acceleration. Okay, so G, I'm going to say, is equal to G, our gravitational constant, times the mass of the planet over the radius of the planet, all squared. Okay, so how did I get to this equation? Okay, so it's kind of like a proof. Okay, so if I have some big planet and some small mass, right? So I've got, this is my planet. So this is where I want to calculate the gravitational acceleration. Okay, so I'm going to label this thing big M. Okay, and my small mass is just mass M. Okay, so from Newton's laws, we know that F is equal to G M1, which is going to be a big M, small m, over the distance between them squared. Okay, and from Newton's second law, we also know that Fg, so this is Fg, force due to gravity, is equal to mass times gravity. Okay, so these two things are the same thing, so I can equate them. So I'm going to say mg, so this is for that small object, right? Mg is equal to g m over r squared. The m's cancel, and I'm left with the equation I wanted, which is g is equal to my gravitational constant times the mass, and the big M was the mass of my planet, r was the radius of my planet, all squared. Okay, so not too difficult. You probably don't need to know how to prove it, but it's an interesting proof and it's quite simple. So there you have it. Okay, and now we'll just do an example on this. So let's say the radius. Okay, so let's say the radius of Venus is 1,6 times 10 to the 6 meters, and it has a mass, and its mass is equal to and it has a mass of 7 times 10 to the 23 kilograms. Okay, so calculate the theoretical value or theoretical acceleration on what planet do we say? On Venus. Okay, so I'm just going to use the equation I had. So g, the theoretical acceleration, is equal to g, my gravitational constant, times the mass over the radius squared. So g we know is 6,7 times 10 to the minus 11 times the mass, which was given as 7 times 10 to the 23 kilograms, over r squared. R was 1.6 times 10 to the 6, and all of that squared. Again, emphasizing the need for brackets. Okay, so if I put this into my calculator, let's see what I get. Okay, so G I get is equal to 18,32 meters per second squared. Okay, remember, acceleration has units of meters per second squared. Okay, so this seems quite high, probably because I made most of these masses and whatnot up, so it's probably not that high. Yeah, I mean, that's pretty much it. There's nothing much to this this section. These are the kinds of questions you can expect. I hope I've gone through everything. I think I have, and yeah. So thanks for watching, guys. I hope you find this useful. If there's anything that's unclear, leave a comment or something, and I'll try clear that up in a future video. Okay, thanks for watching, guys. Cheers.